All right, so we'll get started. So we were looking at linear regression, right? So I'm going to take a step back and then move on. So this is the recap of what we have seen so far. Standard equations for linear regression. We saw how to derive these, and then we also saw how to do it in a stochastic gradient descent kind of manner, or gradient descent kind of manner, instead of doing a direct inversion, right? So that all is good. But then we were looking at issues with linear regression, right? Linear regression is a very powerful method in statistics and econometrics and quality control, wherever they deal with small amounts of data. But for machine learning people, we are not very happy with it, and there are a few reasons. Reason number one, it is susceptible to outliers, and I did give a demonstration last time that if your training data has some outliers, then your linear regression, the way it is learned using these equations, using this formula, tends to get impacted by very few outliers. But then we also saw one way to not get impacted by the outliers, called a method called robust regression, in which the idea is that instead of saying that your y is a normally distributed variable, we say it is a variable which is distributed according to a Laplace distribution, right? So we change the distribution. The effect that it has is that Laplace distribution, the error is not a square, the error is a modulo, which means that the impact of the outlier gets, lessened a little bit. All right. So that is one issue, and we know how to figure that out. The second issue is that sometimes people say that it is too simplistic because it is assuming a linear relationship between inputs and outputs. In many cases, that might not be true, especially when you move to higher order data, higher dimensional data, right? So what can we do in that case? So that issue is also known as underfitting. I have talked about overfitting, where you have a very complex model which does very well on your training data. The other extreme is underfitted data, which is too simple, right? So sometimes linear regression can be thought, or it can be too simple for the problem at hand, right? So one way to handle that, so how to get non-linear, and then there are other issues. One is, and we'll talk about all of those. So it is known to be unstable, even when, let's assume that the linear relationship is fine. If your attributes are correlated, we will see that it becomes very unstable, the results. And the fourth one is that if you have a lot of attributes, and maybe some of them are useful, some of them are useless, but you don't know beforehand, then linear regression can get confused by that. So automatically, there is nothing inside linear regression which can make it select the best attributes. All right. So which means that after doing the linear regression, if you look at the coefficients, it might not be easy to interpret them because you don't know if linear regression has, if some of the attributes are useful or not, right? So we will look at that as well. Okay. So let's handle these issues one by one. We have already done one. So let's move to two, which is too simplistic. So one way to go away from linear regression is say, how about we learn some non-linear curves, right? So how can you do that in linear regression? And we talked about it yesterday on Wednesday. Is we can do something called basis function expansion, all right? Which means that instead of having x, we replace it by non-linear functions of x. So I'm going to give you a example here. After every class, I keep losing my pens. I'm down to this pen. I got it from some hotel. Anyway, all right. So you in your training data, typically you're given this, right? You're given some x's and some y's. Let's say your x is in just one dimension, right? Which means that the training data can be plotted on this 2D plane, right? This is x, this is y, and let's say this is your some training data, right? Now, if you just do linear regression, it would probably learn a line, but you can see that maybe the line is not the best answer, right? So one thing what you can do is you can say that instead of having, so let's say this is your training data. So the training data was 0.4, and for that 0.4 y was 0.3, and then it's 0.5, 0.6. These, I'm just making these numbers up. 2.15 and so on, right? So what you can do is, instead of having x, you can create a new data set in which you apply some functions on this x, and you can apply many functions. So for example, here I'm going to apply functions. I'm going to replace x by a vector which is x to the power 0 or 1, x1, x to the power 2, and x to the power 3. Okay, which means that my data will become 1.4 0.4 square, 0.4 cube, and then the y stays the same. Y is 0.3, so this is y. And then so on, right? So essentially what you're doing is you're getting new features, which are some functions of your original features. And we will see that because these are non-linear functions of your x, what will happen is that now when you do linear regression on these features, the resulting line in this higher dimensional space will actually look like a curve, right? Because essentially what will happen now is that this is your new x, right? So you can think of this as, let's call it x prime, right? And y. So this is your training data now. So now you will learn a w. When you learn a w on this training data, your w will not have two values. I mean, if you had done linear regression here, with the bias, your w would have two elements, right? But now your w will have four elements, right? So that means that it is no longer a line in 2D space. It's actually a plane in four-dimensional space, right? Yes, go ahead. Yes. In fact, that's going to be the next topic, right? So the question is, are there any issues with this kind of expansion, right? Or are we allowed to just go as high as possible? And the answer is definitely there is an issue, and that is going to motivate our next discussion, right? So let's first quickly look at what is the effect of this, and I'm going to show that to you. All right, so this is also known as basis function expansion. Essentially what we are doing is we are expanding our feature space to higher order by applying some function. So each one of them is a function, right? So, but these need not be the only functions that you can apply. You can also do sine of x, or some exp of x, or log of x. You can do anything, right? So it's a basis function. If you are only using these, then what happens is what you're doing is polynomial expansion, right? So that's called polynomial expansion. Sometimes, let's say your original data might have been 2D, right? So instead of having x and y, maybe you had x1 and x2. So assume each of your x is actually in R square, right? Which means that your training data would have looked like this. There was an x1, x2, and y, right? And these would have some values, 0.4, 0.3, and that's a target, and so on, right? Then you could be creative. You can compute new features. For example, you could do a polynomial expansion only on x1 and only on x2, or you could do some combination. Maybe you could create a new feature which is x1, x2, or x1 divided by x2, or something like that, right? So each one of them will have some impact. All right, so let's see what is that impact. So I'm going to switch to our notebook. So this is still the same notebook from last time, so that I've added more parts. Ooh, sorry. So we have seen all of these, right? We have seen the impact of outliers. Now we'll see how robust regression works. All of this, right? So now let's look at how linear regression works. All right. Well, okay. So I'm going to quickly go through these examples. Okay. So what I'm doing here is I'm creating some data first. Okay. So I'm creating some data so that I can fit a curve. So essentially, I took a mathematical function. Okay. So essentially, what I'm saying is my y is some non-linear combination of x. So it's essentially 0.5 pi x cos of 0.5 pi x or cos of pi x by 2. Okay. So that is my actual y, but that's, I won't tell it to the linear regression function, right? Because we want it to learn that, right? So I do that, and then I add some noise to it just to make it a little more interesting. So this is my y, my x is just a bunch of random numbers, right? And then I learn linear regression. Here I'm using the sklearn linear regression. So I fit it, right? And this is what I get, this line. Okay, so this is my data, and this is my linear regression. So this is clearly underfitting it, right? So now what we do is we do what is called polynomial expansion, right? So in sklearn there is a function called polynomial features where you can do that expansion. So the thing that I said, 1 through x to the power. So here I'm doing x to the power 12, right? And then I run linear regression on those features. Okay, so in sklearn there's a very nice command called pipeline, or a nice method called pipeline. What that lets you do is create a analysis pipeline. So what this is doing is it's saying do this first, which means do the polynomial expansion first, and then put linear regression on top of this. So it's easier to handle, right? You could have done it manually as well, but I'm using pipeline because it's easier, more elegant. So in future, if you're using sklearn, do consider using things like pipeline, right? Okay. So once I do that, this is the curve that I get, right? So the way we are able to look at this curve is because linear regression doesn't really give you the equation, right? It gives you the coefficients. So the coefficients can then be used to plot this curve in this space. And of course, this curve will have a nonlinear form because we used a power 12 polynomial expansion. What you will see is that if you keep changing this degree, right? So of course, if you set degree to be 1, then if you set degree to 1, then what you would learn is linear regression, right? The same line. But if you keep increasing, so once I learn degree 2, which means that I'm trying to learn a quadratic polynomial, and then so on. So as you keep increasing the complexity, it will keep making it more and more complex. So what you see here is, as you're increasing the complexity, it is trying to track the data. So it's trying to overfit, right? So being adventurous as we are, we can increase it much more. And here what you see is the scale gets changed a little bit, but this curve actually perfectly fits the data, right? But that's not what we want. So as Dana was saying, there are perils of doing this, right? You can't keep increasing your degree. Let's keep it at 12. 12 looks much nicer. All right. So how can we control this? All right. So clearly this is not a good way, but we do want the non-linear aspect. We do not want to stick to so we do not want to be here. Of course, this is underfitting, and we do not want to be here either. This is overfitting. So we want to be somewhere in the middle. So now we will see how to sort of handle those issues. Any questions so far? Okay. Yeah. So yes. Yes. Don't use anything from that sklearn, not SciPy, by the way. But yeah, you can verify the results. Yes. Yeah, sure. All right. So how do you control overfitting, right? Now this is a general problem. So this looks like a general slide. So one way to control overfitting, of course, is to use simpler models. As I said, you can use linear regression, but that might lead to underfitting. Another way is to keep using complex models, but regularize it, just like you guys did in neural networks, right? So you were using neural networks, which are fairly complex. They learn nonlinear relationships, but then you put some regularization, and you did see that effect, right? That as you regularize more, your generalizability is better, which means you do better on unseen data, right? So in general, for classifiers or regression methods which have this form in which you are trying to minimize some error, we typically add a regularizer, right? We add a regularization term, which means which is equal to the penalty that you pay for the complexity, which means that here, if you come up with a model, or if you learn weights which make this very small, right, you might pay some extra cost here. So you have to, so this optimization function now will try to set a balance. It will try to do trade-offs. So it cannot go too complex, even though that makes this small, because if it does that, it would have to pay some penalty over here. So that is the idea behind regularization, right? So R here is a general term, and then we will see how different R's can be used, all right? So these are two very popular examples of regularization. So here, what I have done here is I have kept the weight, this is the loss function for regression. This is the squared loss, right? Y minus yi hat, or y minus w transpose x square. But this is our regularizer, right? So this is one form. So the R that I talked about here has become the L2 norm, right? So this is a vector, and this is the L2 norm. The L2 norm is essentially you take the square of each element and add it up, right? You can also write it as W transpose W, which means the same thing, right? So typically this is how we do one type of regularization. So what this will do is it will prefer solutions in which the total sum here is smaller, right? Because if it otherwise it will have to pay some penalty here. This alpha, actually I should have written lambda because we have been using lambda more, is the trade-off term which you have looked at in neural networks as well, which tells you how much you prefer simpler models and how much you prefer low training error, right? This is called ridge regression, right? Ridge regression is also known as L2 norm regression because there's an L2 norm here. In statistics, we also call it Tikhonov regularization. I'm assuming because Tikhonov came up with it, all right? What we will see is that ridge regression not only controls the overfitting, but it also has another nice property, which is it helps in reducing the impact of correlated input. So don't think about it too much now, just wait for 2 minutes and I'll explain that. There is another type of regularization in which all you do is you change this function. So instead of having a L2 norm, here you use an L1 norm, okay? So this is, so W with 1 bar means that you are just taking a sum of absolute values of your weight coefficients, right? So L2 norm, we write it like this, right? You can also write it as summation Wi square I equal to 1 through D, and you can also write it as W transpose W, right? L1 norm, like this, also can be written as absolute value of W, all right? Then you can have many other norms, right? You can have L3 norm, L4 norm, L infinity norm. So there are all kinds of norms that you can decide, and each one, yes, go ahead. I'm sorry, go ahead. L2 norm, not here. Well, so if we call it a norm, we need a square root. But if we are when we use it for the regularization, we just use this form, the squared form, because that is easy to, because later I'll tell you, because we have to take the derivative of this. So it will be easier then. But yeah, you're right. When we talk about norms, we usually have a square root there. So yeah, so these are two types of normalization. But in practice, you can come up with any other normalization function. You can say or any other regularizer. So you can say my RW is something else, anything. In fact, if you track some of the recent or publications in computer machine learning, you will see a lot of papers that essentially come up with a new form of regularization, which has some new property, right? So all of the regularizers have one basic responsibility, which is to control overfitting. But because of their functional form, sometimes they have some other nice property as well. And we will see two of them. So, all right, any other questions? Okay, so let's keep moving to our regularizer here. All right, so this L1 is also known as lasso. Okay, so you would hear this term often. It stands for least absolute shrinkage and selection operator, and I'll tell you why it is so. It was devised by Tipshirani and Hastie, these people in Stanford Statistics Department. The one nice thing about lasso is that besides controlling for complexity, it also does feature selection, right? And we'll come to why that is so. But because of that property, this is a very highly used regularizer, all right, or regression method. All right. Yes. Right. So L2 norm is a standard statistical concept, right? So if you have a vector, the L2 norm of that vector is essentially just the sum of squares of those values, and then you take a square root of that. L1 norm is just a sum of absolute values. So those are just standard core statistical terminologies. Here we are using that to do our regularization. So when we use the L2 norm, we call it L2 regularization, right? Okay. So now let's look at each one of them, because I said that it has all these nice effects, right? So the first thing I want to show you is how does ridge regression help you control the complexity. So in sklearn, there's a function called ridge, right? However, in your assignment, you will have to write that function. But here I'm just using that function. So what this does is, you learn this, right? And then when you run it on this data in the same way. So I'm still doing the polynomial expansion, and then I'm applying ridge regression to it. What the effect it has is that suddenly this has become simpler. So if you notice up here, right, I'm still using 12 features, but because of this this ridge regression, it is controlling the complexity. So it's still non-linear, so it is not underfitting, and it is not too complex. Yes.
Are you applying the ridge regression to the polynomial one?
Yes, yes. So if you
it looks like the polynomial regression where the degree was 2.
Exactly. So it looks, but it's not exactly the same, but it has the same effect. So essentially what it is doing is, it is trying to, it has mapped data to 12-dimensional space now, right? But it is not going to learn that complex bound. It's going to simplify it. So it might look like a second order polynomial, but it need not be. So that is the point. So in fact, so what you can do is, let's say you do 24, right? So even then, it kind of has that effect, all right? If you closely look at this function call here, when I create this regression method, right, I specify alpha. Alpha is that alpha. So you can set it to different values and play with it. So let's say I set it to a smaller value. Oh, not much change. Right. So if you choose a smaller value, it would regularize it less, right? Because if you remember the equation that it is trying to solve, this alpha, basically if alpha is smaller, it means that you are preferring solutions which have lower training error than the complexity. But if you increase the alpha, right, so if I make alpha to 1, then it's going to make it even more simpler. So it's going to regularize it more. So if I make it 10, right, it suddenly starts looking like a line. Yeah. So that is the effect of alpha and ridge regression. Any questions so far? Yeah. Yeah, I'll come to that. So let's move to that actually. So this is the exact loss function for ridge regression. So this is your J, right? So this is the training error. right? Yi is your true label or true target value, and W transpose Xi is what you predict. So this, the sum of this for all of your training data, that becomes your training error. Plus, now I've used lambda here. I use alpha here because it ties with sklearn, but in our discussions we have always used lambda. So it's lambda by 2 times the norm, right? Now let's see how to learn the W, because what we are saying is that this is our new loss function, and now we want to find the W that minimizes, right? We did this for our regression, but in regression there was nothing here, right? We only had this part and then we minimized it. Yes. Two twos and two bars, right? Well, the bottom two means that is the L2 regularization, L2 normalization. The top two means that we are going to use we are not going to do the square root. Because if I just do the bottom two and these two pipes, that means I'm going to do the actual norm. But don't worry about this part. I mean, this is just terminology. I'm going to rewrite it in a different way here for us to solve, okay? So now what we are going to do is derive the best W for that loss function. So for ridge regression, what we have said is our JW is it looks like this: 1 minus 2 yi minus W transpose xi square, right? Plus half lambda. So now this could be anything else as well. Instead of half, I could have put 1 by 3. Here I could have put 1 by 4. That's just constants, right? Your answers would change, but the basic concept won't. So let's write it in a matrix way. This is summation. So if y is my vector that contains all of my targets and xw, so I can write it like this, right? Plus half lambda, and then let's write this as W transpose W. That way we don't have to worry about what normalization that is, right? So this is our basic equation. Now we have to find W that minimizes JW, right? So the standard minimizes JW. So the approach is standard. We differentiate it with respect to W, and we open this up. So this part we have already seen in the linear regression part. So I'm going to go fast on that. So d by dw of JW, right? You can open this and do all of that business. What will happen is that it's going to look like this. It's going to be W transpose xt x w dy dw of that, because this I'm going to ignore the one that comes because of y, because that's constant, minus half dy dw 2 times, right? Because this is going to get multiplied by that one, so it's 2 times W transpose x transpose y, right? If you don't follow this part, refer to our Wednesday's calculation. So this is where but the new part comes here, which is plus d by dw of half is outside, lambda W transpose W, okay? This, of course, we have seen from matrix cookbook. This looks like W transpose x transpose x, twice of that, minus half times 2 times x transpose y, plus this is lambda is constant, lambda goes out by 2, and this is actually 2 times W. Here? Yeah. Here? Yeah, this is times. I don't know. So what will happen is all the twos will go away. All right? All right. And I'm going to just rearrange it because that way it will be easier for me. this can be written as this as well, because this is what 1 cross D, right? So this whole thing is a scalar, minus x transpose y plus lambda w, right? Now you will see why I had a half here earlier, just so that when I do the differentiation, the 2 cancels with this 2. That makes the math cleaner, right? Then we set it to 0. So we set d of dw of jw equal to 0, implies that this whole thing is 0, which means I'm going to put all the terms that have w on one side. Right? Now what I'll do is I'll take the w outside because w is common. But when I do that, a strange thing will happen, which is I will have to write it like this. Okay? I is an identity matrix. Identity matrix is basically a matrix with all zeros, just ones in the diagonal, right? So it's like identity. To multiply anything with I, you get the same thing back, right? The reason we get that I is because because this thing is a matrix, right? So this thing is if you look at this one, right? So this is D cross D, right? If I don't put the I, then you are basically adding a scalar to a matrix. That won't work. So that's why you put an I, okay? And so W, I take this here, so that becomes X transpose X plus lambda I inverse X transpose Y. So this is our estimate for the optimal W, which minimizes this error. So now if you compare it to the solution that we got for linear regression, you will see it looks pretty much the same, except there is this term here, right? So for linear regression, it is only this much. So all we did is by adding the regularizer, we added this part here. So you still need to do the same kind of inverse and everything, all right? So that is the estimate. Any questions so far? Yes. No, identity matrix is a matrix which has ones in the diagonals and everything else is 0. Right? Because the effect of identity matrix is that if you have any matrix A, you multiply it with I, you get A. Right? Inverse of I is I. Transpose of I is I. It's like number 1. But you need it to make it consistent. Otherwise, you will be adding a scalar to a matrix. All right. So any questions with that? That's fairly standard, right? Okay. It turns out that if you come up with any other regularization, right? So if you, instead of this, if you put lasso, right, you would have to do this in a different way, right? So let's say for lasso, your JW is actually this. Your JW is half of this thing plus half of lambda absolute value of W, right? So now if you want to find the W, you'll have to differentiate this. Now that's where things start getting a little more interesting, because it's not easy to differentiate absolute values, right? That is why ridge regression is so nice to work with, is because it lets us do this thing, right? When it lets us do this differentiation, this is what we get. But if you have something more complicated like this one, then you can't do a differentiation because this is not a smooth function, right? This is an absolute. Absolute is it sort of at 0 it shows a weird behavior, which means that you can't apply standard gradient descent kind of methodologies there or standard differentiation methodologies. You have to come up with something new. So typically for lasso, they use something which is called block coordinate descent and other methods. So they are slightly more advanced optimization methods that are meant for functions that are not smooth. All right. So in this course, we are not going to use that at all. Right. I'm going to give you some demonstrations of lasso, but we are going to use standard sklearn routine for that. And then in your assignment, you are not supposed to work with lasso at all. Right? Any questions so far? Okay. So now let's move on to some more interesting properties of all of these things. So we have already seen how lasso helps us, also how linear regression helps us to control the complexity, right? Now let us also see some other properties. So as I said earlier, right, ridge regression can also help you deal with correlated variables. So first let us see what is the issue with ridge regression, all right? So let's say what is the issue with linear regression? So let's say you have this linear regression method, all right? So here you have some x, and here is your y. Okay, what I've done here is I only had one variable and I converted it into two variables. So one of the variable is just x and another one is oh no, what am I saying? Right. So here my x has three variables, x1, x2 and x3, right? But your y is only dependent on the first variable and the second variable, not on the third variable. Okay, so when I do the linear regression, I fit it. This is the model that I get. This is the intercept weight. This is the W1. So this is W0, W1, W2, W3, right? So this is fine, right? This looks good because here essentially it kind of tracks the actual model, right? This is close to 1. This is close to 2. And this is close to 0 because it doesn't depend on x3. So here linear regression works very well. But what if I add some correlated variables? So in this example, what I do is I create 3 variables, but all of these 3 variables are actually the same variable with some noise added to them. All right. So, and then my y is the sum of these 3. So in reality, even though y is x1 plus x2 plus x3, it can also be 2 times x1 plus x3 because they're all the same, right? It could be 3x1, it could be 3x2, 3x3. And that is what confuses linear regression. So if you keep running it over and over, right? So here what I do is I create this data 10 times, and every time I fit the linear regression, and I had this helper function that I wrote to, I lost it. Where is it? Yeah. So every time I learn a linear regression, what you will see is that the coefficients change quite drastically. So in this run, so every time the data is similar, right? The data is essentially all these 3 attributes are correlated. So what you will, and every time the change that is happening is that I'm adding different types of noise in it. So technically it should learn the same model, but because linear regression is not really meant to do that, it keeps changing. So here the impact of x2 is close to -1, impact of this is 2, close to 2, and this is 2. So what you will see is that the sum of these coefficients will be close to 3 because that is what y is, right? So y is actually 3 times x of seed, right? So but it's fairly unstable. So sometimes it gives equal weights or close to equal weights to all of them. Sometimes it gives higher weight to 2 of them and low to 1 and so on. So that's sort of a bad property of linear regression. However, if you do ridge regression in the same setting, what you will get is fairly stable results. Okay, so if you see ridge regression in the same setting, the coefficients are very stable, close to 1. Of course, there's some change, but they are all close to 1. All right, so that is one nice property of ridge regression. So in reality, in practice, when you're doing regression, and if you feel that, okay, maybe your inputs are correlated, ridge regression can help you in that sense. Okay, it will also help you in controlling the complexity. That is its original job, but it will also help you in this case. Any questions so far? All right, now let us look at the property of lasso. Okay, So of course, we have already seen that lasso helps in doing the overfitting as well. Oh, we haven't seen it actually. So this is the same example like I showed it for rigid regression, but with lasso, and you see that lasso also helps you keep things simple. So that is fine. It's supposed to do that. But it also has this other beneficial property which makes it so popular, which is that it induces sparsity. So sparsity means that in your solution, right, the solution is the vector, right, the weight vector is your solution. What lasso does is the way, because it optimizes the way the optimization function is set up, right, because of that absolute value of w, the penalty there, it gives very sparse, it prefers sparse solutions. So because of this thing here, the weights that you will get, so if let's say I plot the weights as bars, it tends to prefer solutions that look like this. Let's say you had 5 attributes, only a few of them are non-zero and everything else is 0. So that's the kind of solutions it prefers. Or maybe it will find something like this, right? So these are what we call sparse solutions. If you see linear regression or ridge regression, they prefer the solutions there would look more like this. Everything is something. All right. What ridge regression typically tries to do is it will make everything small, because it's the penalty there is summation wi square, right? Which means that anything, if anything is large, it has to pay quadratic of that as the cost, right? So it tends to keep everything small. But here, because it's the penalty it's paying is this, it wants to make as many of them 0 as possible. All right. So the benefit of this is that it helps you do feature selection, because now you can look at the coefficients that are non-zero and it tells you, okay, these are the important features. All right. Whereas here you won't be able to do feature selection. So if in lasso, the benefit is that if you have very large number of features and maybe a lot of them are not important, lasso will help you weed out those ones. And in practice, that's what happens, right? In reality, you tend to use a lot of features without really doing due diligence in removing the bad ones and everything. So lasso will help you do the job for you. All right, so I'll quickly give you a demonstration, and then we can continue this discussion on Monday as well. So here what I've done is I've loaded a data set which is a real data. So in sklearn there's a package called datasets which has a lot of these datasets built in. So Boston dataset is a housing market data. So it was collected way back, but it's a very nice dataset. It's basically you're trying to predict prices of houses based on their different properties, like what is the size, where are they located, and so on, right? So that is our data. If I fit linear regression to it, right, without doing any lasso or anything, and I also do some cross-validation to see how well it works, this is what I get. So the cross-validation error is this. Cross-validation is similar to what you did for neural networks, which is just a validation, right? So this is the error that you get on test data, unseen data, and this is your model, right? So the thing that I want to tell you is, these are the names of the attributes, is that it's very hard to interpret this model, right? Everything looks important, right? But when you do lasso, you get similar error, but your model now is sparse, which means a lot of these entries are actually 0. So now it's easy to explain, right? Because we have only the important ones which are non-zero. So you can also compare it visually. So this is what you get. So these are the weight. This is basically all the weights, and the red ones are the values for the weights that are coming from linear regression, and green ones are the ones that are coming from lasso. So you see that there are only a few big green ones, but in linear regression there are a lot of red ones, high red ones, right? So that is the impact of lasso. It controls the sparsity, which makes it easier to interpret, as well as it keeps it simple. All right. So yeah, any questions so far? Yes.